I'm Kaisei KAJITA of Japan Broadcasting Corporation. I will talk about the constant size signature scheme with tighter reduction from CDH assumption. This is joint work with Kazuto OGAWA of NICT and Eiichiro FUJISAKI of JAIST. First, I will explain about the digital signature. Let's say Alice sends a message to Bob via the internet. In this case, if there is an attacker named Eve, he may impersonate Alice and may change the message. So Bob needs a way to confirm the message is real from Alice. This is a digital signature. And the secret signature key is used to generate a signature for the message, which is sent with the message. Then by the public verification key, Bob can verify the digital signature. Next, I talk about the digital signature security. The security of the digital signature is based on the assumption that is breaking a signature is as difficult as to solve some difficult problems. In other words, the difficulty of breaking a digital signature is reduced to the difficulty of solving a very difficult problem. This is called security reduction. The difference between the original digital signature and the difficulty of the hard problem is called the reduction loss. So the smaller the reduction loss, the more secure the scheme is. And there are two types of difficult problems, digital problems and search problems. So digital problems determine the pitch of 2 is correct, and they are widely used as a basis for security. On the other hand, such problems are to find the solution by yourself and are generally considered more difficult than digital problems. So a digital signature scheme based on the such problem is generally more secure. So next, I will now explain the design concept of our signature scheme. We construct the signature based on the more secure such type program, so rather than the digital program. However, under some conditions, the theoretical bound of the reduction loss order of Q is already known for signatures based on the such programs. We focus on the signature scheme of Bohr et al. To achieve a reduction loss to that exceeds this theoretical bound. So this is our design concept. So this is our result. First, look at the reduction loss of the signature scheme of Bohr et al. If we can make the difficulty of breaking the scheme close to the difficulty of solving such problem, and we can achieve the tighter reduction loss. So in Bohr et al. Reduction loss, the difficulty of scheme and the difficulty of scheme and the difficulty of such problems are far due to these coefficients and terms. So we review the causes one by one. So first, why for the green term, epsilon PRF, the loss is due to the use of pseudorandom function, and we reduce the loss to 0 by constructing the scheme without the pseudorandom function. And for the blue term, we reevaluated the probability to the exponentially negligible. And for red term, we improve this probability to achieve this minimum. So in this way, we have achieved and proved the reduction loss of our scheme is order of Q over E. So in other words, we have constructed the first signature scheme that surpasses the theoretical bound of such type problems of order of Q.